Hello, this is Dr. Grande. Welcome to my video on selecting the correct statistic. As always, if you find this video to be helpful, please like it and subscribe to my channel. I certainly appreciate it. Here I'll be looking at how we go about selecting a statistic to test our null hypothesis. So we start with a research design, we collect data, we form a research question as part of the design phase, and then create a hypothesis that we want to test. And here I'll be reviewing a number of statistics and looking at what null hypotheses they test, and also looking at some of the constructs that we use to decide what statistic to select. There are a number of ways to go about selecting the correct statistic. You have flowcharts where you can track number of variables and design, number of dependent variables, for example, how many groups in the independent variable. Here what I'm going to do is I'm going to review some of the key constructs that affect our decision to select a particular statistic over another, and then go through some of the more popular statistics and show you how these constructs align for that statistic. There are, of course, additional statistics that will not be covered as part of this video. However, I did try to get all of the statistics that we would see frequently in counseling research covered in this video and in terms of these constructs I'll talk about here. So again, a statistic is used to test the null hypothesis, and that null hypothesis is specific to that statistic. Some of the constructs that affect what statistic we select, you have variables, I'll review those, the design, the level of measurement, and of course the assumptions of that statistic. So we may have a certain null hypothesis that we want to test that will answer a research question that will lead us to a parametric statistic, but the data could fail to meet the assumptions of that statistic. So in that case, we may look to transform a variable, or we may switch to a non-parametric alternative. So in instances when I'm talking about a parametric statistic, if there is a non-parametric alternative, I have that listed in the slide as well. If you fail to meet the assumptions for a parametric statistic, you don't always need to move directly to a non-parametric statistic. Sometimes there are ways to manipulate the variable, like a transformation, that will allow you to continue with the parametric statistic. I'm not going to review the assumptions of all these statistics here, although many of the assumptions are fairly similar for parametric statistics. A popular assumption is the assumption of normality. Another popular assumption is the assumption of homogeneity of variances, also known as homoscedasticity. It's important to keep in mind as well that non-parametric statistics also have assumptions. Usually they're much easier to meet than parametric statistics, but they do have them. So let's take a look at the first level here, which should be variables. So this would be the first item you want to consider when you're trying to work out what statistic to use. So I have three types of variable here: independent, dependent, and a covariate. So what you want to ask of your data and your research design is how many independent variables do you have, and how many levels do you have for each one. For example, a relatively simple design would be one independent variable with two levels. For example, in counseling research, you could treat depression with cognitive behavioral therapy as one level of an independent variable treatment, and another level may be psychodynamic therapy. And clearly we can move up in complexity from here. We can have multiple independent variables with varying numbers of levels. You could have one independent variable with two levels, another independent variable with 4 levels, another independent variable with 10 levels. You also want to consider the level of measurement with an independent variable. So primarily when I refer to an independent variable here in this video, I'm talking about groups. So it would be at the nominal level of measurement, like like CBT and psychodynamic. However, there are statistics available for instances where the independent variable is measured at a continuous level. And I'll talk more about the levels of measurement here in a few moments. Then we have the dependent variable, and we have the same questions about the dependent variable. How many, and what is the level of measurement? We typically do not have dependent variables that have multiple levels, for example, a nominal dependent variable. However, that is possible, and there are statistics available to handle a categorical dependent variable. Again, I'll talk about that in a few moments. And then for the last type of variable, we have the covariate. Now, the covariate is only used in a few specific statistics. I included it here, though, because it is an important construct. You have a continuous variable that you believe is connected to the outcome variable, the dependent variable, and you want to control for the effect of that covariate. So you want to have an independent variable that's related to a dependent variable, and you want to see the effect that independent variable has on the dependent variable. For example, if you have a number of groups for your independent variable, say 4 groups, you may want to see if one or more of those groups stands out in terms of how it's measured on the dependent variable. And at the same time, there could be another variable, measure the continuous level of measurement, that predicts the dependent variable. It has an association with the dependent variable, and you want to control for the effect of that covariate, that continuous variable, so that you're only seeing the effect that the independent variable has. You may also see a covariate in pretest, post-test designs, and often the covariate is used as the pretest variable, and the dependent variable, of course, as the post-test variable. So as you're trying to determine the variables for your research design, it can sometimes be confusing to distinguish the independent variable from the dependent variable, particularly when we get into between subjects and within subjects designs. In general, we can think of the independent variable as the variable that we manipulate as part of an experimental design. For example, a common independent variable is treatment, like the example I used before with one level being CBT and another level being psychodynamic. That's the variable that we manipulate. We can assign participants to both of those levels of that independent variable treatment. What can be a little more challenging to understand is what happens when you have a variable that you're using as an independent variable, but it's not a variable that you can manipulate. For example, if you have participants divided up by where they live, and you want to see if there's any differences in how well they respond to treatment based on that geography. So perhaps you divide it up into the names of towns. That would be an independent variable, but it's not a variable that you can really manipulate. You can't ask the participants to move from one town to the other. Or, for example, looking at a continuous variable. A good example there would be age. You can't assign somebody to a certain age. They come in as a participant to your research study, and they are whatever age they are at that time. When we treat a variable like that as an independent variable, we refer to it as an attribute variable. In terms of statistics, it's treated identically. But in terms of research design, an attribute variable cannot be manipulated. An independent variable can be manipulated. And then let's take a look at the dependent variable. So the independent variable is the variable we manipulate, and the dependent variable is our measurement. Typically, the value for the dependent variable in counseling research anyway comes directly from a psychometric instrument, like an inventory designed to measure levels of depression or anxiety. The dependent variable is also referred to as an outcome variable, and sometimes it's referred to as a response variable. Now let's take a look at design. So here, for the purposes of selecting a statistic, I'm using just 2 constructs within design, and that's between subjects or within subjects. So you have unrelated groups, that's between subjects. That's when you have different participants in each group, and related groups. And related groups is where you have repeated measures. The same participant is measured more than once. These are two popular design strategies that relate to the statistics that I'll be covering here. So let's review an example to determine if you have unrelated groups between subjects or related groups within subjects. Let's say you have a specific counseling treatment that you believe lowers anxiety, and you gather participants, and you have 30 participants in one room and 30 participants in another room. So you have two groups. You measure their anxiety levels, and then with one of the groups you deliver your specialized counseling treatment, and you don't do anything for the other group. And then again you take a measurement afterward. Those groups are between subjects. That's an unrelated group design. You're comparing the anxiety levels of a group of participants with the anxiety levels of different participants, unrelated groups. Now let's consider that you have a room with 30 participants, and you measure their anxiety levels. Then you deliver the specialized counseling treatment, and then you measure the same participants' anxiety levels again. Those are related groups. They're the same participants being measured repeatedly. Typically with statistics, we're going to be using one design or the other. So either we have unrelated groups or we have related groups. Although of course there are exceptions to this, where you can mix unrelated and related groups in the same statistic. However, for the most part, we'll just be using one or the other. And now moving on to the level of measurement. In terms of determining what statistic that you need to use for a particular analysis, it is important to determine the level of measurement for the independent variable or independent variables and the dependent variable or dependent variables. If applicable, you also need to look at any covariates. We have 4 levels of measurement we typically use in statistics. And we can think of the nominal level, the first level, as the most basic, and the ratio level, the last level, as the most complex. So we move from nominal to ordinal to interval to ratio. It's moving from basic to the most complex. So let's start with the nominal level of measurement. Nominal means in name only. And this is a level of measurement where all we have is the name. So for example, genres of music. We can't rank genres of music. They just have names. There's no way to rank them. There's no way to determine any meaningful distance between the genres of music in name only. Nominal is the most basic level, and it's a fairly common level of measurement for an independent variable. For example, with the CBT and the psychodynamic levels of the independent variable treatment, both CBT and psychodynamic are counseling treatments, and that's a nominal variable in name only. When we move to the ordinal level of measurement, we retain all the properties of the nominal level of measurement, and we add the ability to rank or order the observations. So using the example of genres of music, say that you have 5 genres on a survey and you give it to a participant and you say rank these from 1 to 5, and you have then the genres ranked from 1 to 5 in terms of how well the participant likes the genres. So they rank their favorite at the top and their least favorite at the bottom. You could have a participant that really likes all music, so the distance between those ranks could be very small. Or you could have a participant that likes one of those genres of music but doesn't like any of the others. So one is really high up and the other 4 are compressed down low. But again, just looking at the ranks, you don't know that. You can't figure out a meaningful distance between those observations. Now of course you could get around that by restructuring the survey by asking a different question, like rank how much you like this genre from 1 to 20. And that brings us to the interval level of measurement. The interval level of measurement retains all the properties of nominal and ordinal and adds this idea of a meaningful distance between observations. So staying with the same example, say that you ask a participant to rank the genres of music on one survey, that's the ordinal level of measurement, and on another you ask them to assign a value to each genre. Now the distance between the observations has meaning. You can interpret it a little differently than just ranks. Another example of an interval level of measurement is the Fahrenheit scale for temperature. You have a meaningful distance between observations. However, you lack a true zero, meaning on an interval scale, you do not have a true zero. Looking at the Fahrenheit scale of temperature, there is a zero on the Fahrenheit scale, but it's not a true zero. It doesn't represent an absence of any heat. Ratio level of measurement has all the characteristics of interval, ordinal, and nominal, and it also adds that true zero. So thinking in terms of like the Fahrenheit scale, where you don't have a true zero, you'd have to move to something like the Kelvin scale. On the Kelvin scale of temperature, 0 represents an absence of heat, so that scale has a true zero. So an important point here about these levels of measurement: interval and ratio, for the purposes of statistical analysis, are oftentimes treated the same. We refer to interval and ratio as continuous. So if you have an interval level variable or a ratio, both of those are at the continuous level of measurement. So now, keeping all those constructs in mind, the type of variables, the design, the level of measurement, I'll be moving to the first statistic here, which is correlation. And again, I'm not going to be going through all the assumptions for each of these statistics, but only trying to give the necessary information for determining which statistic is correct based on the research design and the hypotheses. So here we have correlation, and in correlation we have two variables. And notice here that I'm not referring to them as independent variables or dependent variables. They're just two variables for correlation. There is no independent or dependent. You may have one variable that you believe is causal and another variable that is a measurement. However, in terms of the statistic, that won't matter. It's a strength of association measure. That's what a correlation is. Both variables need to be at the continuous level of measurement. So again, interval or ratio level of measurement. The null hypothesis for a correlation is that the population correlation equals 0. And there is a non-parametric alternative to a correlation. If you don't have the variables at the continuous level of measurement, but rather the ordinal level of measurement, you can use a Spearman's rank order correlation. So now moving to the point-biserial correlation. So again, here you have two variables, except in this case you have one dichotomous variable. That's a variable that has two levels. It's a special case of the nominal level of measurement. It just has two categories. And then you have one continuous variable, again at the continuous level of measurement. The null hypothesis here is the same. The population correlation equals 0. It's the same as for the Pearson product moment correlation, the one we covered before. And the point-biserial correlation has an alternative statistic available, and that's the independent samples t-test. So if you have a dichotomous variable, two levels of measurement, you have a continuous variable, a point-biserial correlation, and an independent samples t-test will give you the same result. There's also a non-parametric alternative for the point-biserial correlation, and that's the Mann-Whitney U-test. Now moving on to the independent samples t-test. So here, under independent variable, you just have one independent variable and only two groups, and these are unrelated groups. two unrelated groups. You also have one dependent variable, measure the continuous level of measurement. So the same variable requirements we see for the point-biserial correlation. Now the design here for an independent samples t-test is a between subjects design. So let's say you have participants that are suffering from depression and you divide them into two groups. I'll use the same two groups I used before, CBT and psychodynamic treatment, and then you measure their levels of depression. That's your dependent variable. So your independent variable would be treatment, and your dependent variable would be the level of depression. Again, a between subjects design. A participant can only belong to one of those two groups, either the CBT group or the psychodynamic group. They can't belong to both groups. So it's between subjects. The null hypothesis for the independent samples t-test is that the population means are equal, and you have a couple different choices here for an alternative statistic, of course the point-biserial correlation, and also one-way ANOVA. We usually think of one-way ANOVA as an independent variable that has 3 or more levels, but it can have just 2 levels. And if you perform a one-way ANOVA and an independent samples t-test, you'll get the same result. There's also a non-parametric alternative for the independent samples t-test, the Mann-Whitney U-test, which of course makes sense because the Mann-Whitney U-test is also a non-parametric alternative to the point-biserial correlation. Now moving to the dependent samples t-test. So we had the independent samples t-test, that's a between subjects design, and now we're moving to the dependent samples t-test, also known as the paired samples t-test, and this is a within subjects design. So again, you have an independent variable, you just have one, and 2 groups, but these are 2 related groups, the same participants in both groups, and one dependent variable measures the continuous level of measurement. We often see the dependent samples t-test used with pre-test, post-test designs. So say you have participants coming into a facility, a mental health treatment facility, because they have anxiety, and they agree to participate in research, and you give them a test that measures their anxiety levels, then you deliver some form of treatment, and then you measure their anxiety levels again after the treatment's completed. So the same participants are being measured twice. They receive both the pre-test and the post-test. So it's a repeated measures design, or a within subjects design. The null hypothesis here for dependent samples t-test is that the mean difference between the paired observation equals 0. There's also an alternative statistic here, and that's the repeated measures ANOVA. And we typically think of repeated measures ANOVA as being similar in terms of the design, but you have 3 or more related groups. You could use repeated measures ANOVA with just 2 related groups. We usually think of it for 3 or more related groups. And there is a non-parametric alternative to the dependent samples t-test as well, the Wilcoxon sign rank test. Now we'll take a look at one-way ANOVA. ANOVA stands for analysis of variance. And in inferential statistics, there are a lot of versions of ANOVA. You have one-way ANOVA, Factorial ANOVA, which would be a 2-way or more, so that's 2 or more factors, ANCOVA, MANOVA, MANCOVA. So there are a lot of different types of ANOVA. Here I'll be looking at the one-way ANOVA to start with. And the one-way ANOVA has one factor, one independent variable. And that independent variable typically has more than 2 groups. Usually you have 3 levels to your independent variable with the one-way ANOVA. It will, of course, accept just 2 levels. And when you have just 2 levels, you usually see the independent samples t-test used instead of ANOVA. The one-way ANOVA has one dependent variable, measured the interval or ratio level of measurement, otherwise known as the continuous level of measurement. And the design is between subjects. So let's say they had participants that had anxiety symptoms, and you had different treatment groups, CBT, psychodynamic, and treatment as usual. So that would be 3 levels: CBT, psychodynamic, and treatment as usual. Those are the 3 levels of your independent variable. And then your dependent variable would be a psychometric instrument that measures anxiety levels. Each participant would only be assigned to one of those groups. So that makes it a between subjects design, and that's what we use with one-way ANOVA. The null hypothesis is that the population means of each level are the same. So whenever you're looking at statistics like this, where you have at least one independent variable, and that independent variable has 3 or more levels, you have to understand that the statistic is not going to tell you where the difference is. If it identifies a difference between the groups, between the levels of the independent variable, it's not going to identify where that difference is. To do that piece, we use what's called post hoc testing. And we would select a post hoc test based on the characteristics of the independent variable. For example, are the sample sizes for each group equal or unequal? And there are also a number of other characteristics you have to keep in mind for post hoc tests. So in the example that I've been using, if you get a statistically significant result, looking at the difference in anxiety levels between CBT, psychodynamic, and treatment as usual, you don't know if that difference is between CBT and psychodynamic, CBT and treatment as usual, or psychodynamic and treatment as usual. That difference is not identified by ANOVA. Just the fact that there is a difference somewhere is what the ANOVA tells you. Now you could also have a difference between multiple pairs. So the difference doesn't have to be just between 2 of the groups. The difference could also be between multiple pairs. The one-way ANOVA also has a non-parametric alternative. It's the Kruskal-Wallis H-test. Now moving to the one-way analysis of covariance, one-way ANCOVA. So again, looking at this term, we see that we have one factor, one way, one independent variable, and again, typically more than 2 groups. When we're working with ANCOVA, we can use just 2 levels though if we need to. And we have one dependent variable. It's measured at the interval or ratio level of measurement. So all that's identical to one-way ANOVA. The difference with ANCOVA is you're introducing 1 or more covariates. These are variables that you believe are influencing the dependent variable, and you want to control for these covariates so you can get a clear idea of what impact the independent variable is having. The design, just like one-way ANOVA, is between subjects, and the null hypothesis is similar. The null hypothesis here is that the adjusted means of each level are the same. Now they use the term adjusted because these means are adjusted because of the covariate or covariates. Moving now to factorial ANOVA, and I'm using this term factorial ANOVA, and what this refers to is you have more than one factor. So you could have a 2-way ANOVA, 3-way ANOVA, 4-way, etc. All those types of ANOVA are factorial ANOVAs. So here you have 2 or more independent variables, and each of those independent variables can have 2 or more groups. So an example, building on the prior example, would be one group that's CBT, psychodynamic, and treatment as usual. That's the treatment independent variable. And another independent variable that's gender, and that would have 2 levels, male and female. So that would be a factorial ANOVA, and more specifically, it would be a 2 by 3 factorial ANOVA. 2 levels of the variable, independent variable gender, and 3 levels of the independent variable treatment. Factorial ANOVA also has one dependent variable, again measured at the continuous level of measurement, and it is a type of statistic used with between subjects designs. It gets a little more complex as you move up to Factorial ANOVA in terms of the null hypotheses. It has more than one null hypothesis, and you could think of this in terms of how many independent variables you have. So let's say we're working with a two-way ANOVA, a factorial ANOVA with two factors. The null hypotheses would be that the population means for factor 1 are equal, the population means of factor 2 are equal, and there's no interaction between the factors. Now looking at factorial ANCOVA. Factorial ANCOVA is the same as factorial ANOVA, except we introduce again the idea of the covariate, just as we did moving from one-way ANOVA to one-way ANCOVA. And we look at the null hypotheses. The adjusted means of factor 1 are equal, adjusted means of factor 2 are equal, and so on, and we have no interaction. So similar, except we have the addition of covariates, and we have to change the null hypotheses a little bit. Now moving on to MANOVA, and specifically one-way MANOVA. With a one-way MANOVA, we have one independent variable. And again, there could be a two-way MANOVA, three-way MANOVA. Anything above one way would be factorial MANOVA, which I'll get to in a few moments. The factor here for one-way MANOVA has two or more groups, two or more levels, and what changes here as we move from ANOVA to MANOVA is the number of dependent variables. We have two or more dependent variables. So this is a multivariate analysis of variance. That's what MANOVA stands for, multivariate analysis of variance. These dependent variables must be measured at the continuous level of measurement, and we are working with a between subjects design here. So to modify the prior example so that it works with one-way MANOVA, we have the treatment variable, CBT, psychodynamic, and treatment as usual, and we have that anxiety level dependent variable. If we added now depression, so we want to measure anxiety and depression, so two separate measurements, two separate dependent variables, two instruments that each participant will be taking, we have to move up to MANOVA, multiple dependent variables. The null hypothesis here is that the means of each level are the same, and the means are the same on a linear combination of the dependent variables. So it's taking a linear combination of the depression variable and the anxiety variable, and it's looking at the means in terms of the three groups, CBT, psychodynamic, and treatment as usual. On to one-way MANCOVA, very similar to one-way MANOVA, except you introduce in this statistic the covariate or covariates, and you adjust the null hypothesis using the term adjusted means. And again, it's a linear combination of those dependent variables. All the other items here are the same as one-way MANOVA. Now taking a look at factorial MANOVA. Factorial MANOVA is similar to factorial ANOVA, except you have more than one dependent variable. So again, staying with the example I've been using, here you would have gender at two levels as an independent variable, male and female, treatment at three levels as an independent variable, CBT, psychodynamic, and treatment as usual, and you'd have two measurements, an inventory to measure depression and an inventory to measure anxiety. This is used for between subjects designs, and you have null hypotheses here for factorial MANOVA. The population means of each factor are equal, so again factor 1 are equal, factor 2 are equal, and you don't have any interaction between the factors, between the independent variables. So in this case there'd be no interaction between gender and treatment. Factorial MANCOVA, very similar to factorial MANOVA, except you introduce the covariate or covariates and you change the null hypotheses so that you're using adjusted means. Other than that, there's no differences moving from Factorial MANOVA to Factorial MANCOVA. Now we'll be taking a look at one-way repeated measures ANOVA. So we're moving away from the between subjects designs and moving to a within subjects design. This is repeated measures ANOVA. So you have one independent variable here. That's what the one way is for. And it has two or more groups. And it's not unusual for the independent variable in a one-way repeated measures ANOVA to be time. So you have participants who complete a treatment and you want to evaluate their depression levels, so you measure them immediately after treatment, a month later, and then another month after that. So immediately, and then at 1 month after, and then at 2 months after treatment. So you have, in that case, 3 related groups, and that independent variable is time. Now the independent variable doesn't have to be time. It can also be conditions. So say that you had participants taking some sort of test, and you test them in a room that had a low light level, one with a moderate light level, and one where the lights were very bright. So the condition, the lighting, is the independent variable. That's what's changing, and you are testing the participants in all those conditions. So the same participant is taking that test in all 3 of those conditions. That would be suitable for one-way repeated measures ANOVA. This statistic has one dependent variable, and just like the other ANOVA examples, you have a continuous level of measurement. Unlike the other ANOVA examples so far, this is a within subjects design, not a between subjects. Within subjects, the same participants are measured repeatedly. And the null hypothesis is that the means of the measures are equal. One-way repeated measures ANOVA does have a non-parametric alternative. It's Friedman's ANOVA. Next we have factorial repeated measures ANOVA. So we have 2 or more independent variables, 2 or more related groups. However, you can also mix in unrelated groups here. So you can have a mixture with factorial repeated measures ANOVA of related groups and unrelated groups. We could think of it as within subjects and between subjects. You have within subjects factors and between subjects factors, potentially, for factorial repeated measures ANOVA. So for example, if you had 2 related groups, building on the prior example with the lighting level in the room as the test was being taken, you could also add a sound level, and each participant would have all those combinations of the light and sound. Those 2 constructs, the lighting level in the room and the sound level in the room, would be within subjects factors. So an example of factorial repeated measures ANOVA that has 1 within subjects factor and 1 between subjects factor would be if you had that prior example I was using of a treatment variable at 3 levels and a gender variable at 2 levels. Except now, instead of measuring them just 1 time with the dependent variable, you measure them 5 times over the course of 10 months, so once every 2 months. You'd have the independent variable treatment, the independent variable gender. Those are between subjects. They are unrelated groups. And then you have the independent variable time, which is a related group, the 5 points in time when the test will take place. So when considering the factorial repeated measures ANOVA, this is repeated measures, so you know that one of the factors, at least one of the factors, will be a within subjects factor. And as you start to add other factors, they may be other within subjects factors, or you could have between subjects factors. The null hypotheses for factorial repeated measures ANOVA, the means of the levels of each factor are equal, so again factor 1, factor 2, factor 3, and you have no interaction effect. I'm not going to cover the other types of repeated measures ANOVA here, but there are other types. You can have a repeated measures ANCOVA, repeated measures MANOVA, and MANCOVA as well, just like we saw with the one-way ANOVA and the factorial ANOVA. So now moving on to linear regression. So we've been dealing a lot with independent variables that have categorical levels like CBT, psychodynamic, and treatment as usual. However, you can have an independent variable that's measured at a continuous level of measurement. For example, intelligence or age. You may want to use independent variables to predict the value of an outcome variable. And for this we use a linear regression. If you have just one independent variable, one predictor variable, as it's often referred to with linear regression, that is a simple linear regression. If you have two or more independent variables, we refer to that as a multiple linear regression. In either case, though, you have one dependent variable, and it's also measured at the continuous level of measurement. So an example here for regression could be if you looked at participants that were struggling with substance use disorder, specifically alcohol, and you measured the number of ounces of alcohol consumed in a month. That would be a continuous independent variable. And then you looked at a depression inventory that measured depression levels at the continuous level of measurement. Using those two variables, that predictor variable of the number of ounces of alcohol consumed and that dependent variable of depression level, you may be able to predict the level of depression when you're given that independent variable. And if the participants were using substances in addition to alcohol, you could measure that substance use as well, and those would become additional independent variables. So you could take those independent variables together and try to predict that dependent variable of depression. Linear regressions use a least squares method to draw a regression line through data points, and the null hypothesis is that the slope of that line is equal to 0. So the null hypothesis would be here that your independent variable cannot be used to predict the dependent variable value. So the last statistic that I'll be looking at here is logistic regression. And with a logistic regression, you can have one or more independent variables, and the variables can be nominal or continuous. And for the dependent variable, you have one dependent variable. It's measured at the nominal level of measurement. So the dependent variable, in the case of logistic regression, is categorical. So let's say you had a specific treatment program, and the outcome of that treatment program would be failure or success. So just two levels. So your dependent variable is failure or success. You could use continuous variables or nominal variables or both to predict group membership, the probability of being in the failure group or the success group. And you could use variables like depression level, anxiety level as examples of continuous variables. And for nominal variables, you could use gender, male or female, or treatment that participants received just before this other treatment that you're measuring. So again, you could have CBT, psychodynamic, and treatment as usual, for example. They could be in one of those groups as well. When looking at the dependent variable in terms of logistic regression, if you have a dependent variable, the nominal level of measurement, and it has just two levels, like the example I'm using with failure or success, that would be a binary logistic regression. If you had a dependent variable that had three or more levels, like high, medium, and low, that would be a multinomial logistic regression. And the null hypothesis for logistic regression is the same as what we saw for linear regression. The slope is equal to 0, meaning there's no relationship between your predictor variables and your outcome variable. So logistic regression is the last statistic I am covering as part of this video on determining the correct statistic. There are other statistics available that were not listed here that I did not cover, although the ones featured here are fairly common. I hope you found this video on selecting the correct statistic to be useful. Thanks for watching.